Okay, so I'm going to do another session here on melting because this are the first videos that I've done, and melting is something that I know and feel comfortable with. So before I did a video on the Lindemann criterion, but now I'd like to look at this Clausius Clayperon equation. So according to the Clausius Clayperon equation, we have 1 over the melting temperature times the slope of the melting temperature as a function of pressure equals the change in volume. That's the volume from the solid phase to the liquid phase. This is melting, by the way, not crystallization. So we're always going in the direction of solid to liquid. And then it's the change in volume of the solid to the liquid phase over the latent heat of fusion. Okay. So there's a couple different ways to rewrite this that I'll go over, and then I want to go over just because this is not an empirical equation. This is something that comes from straight up first principles, which is kind of fun. Okay, so if I just rearrange this a bit, what I get is dp dt. So the slope of the pressure as a function of temperature equals latent heat of fusion over T times change in volume, and that equals the change in entropy over the change in volume. Since what we have is our change in entropy is our latent heat of fusion divided by the temperature. Entropy is the amount of disorder in a system and has units of energy. So another form here is we could also express as this function, which we could then integrate. Or we could call that delta S delta V dP. Okay. So now, where does this come from? Well, if you're studying thermodynamics, then you have things called your TDS equations. Right? TDS? So the TDS equations, TDS. So temperature and change in entropy. Okay, so let's approach this from entropy. So we have entropy S, and then we want to look at the change in entropy. Okay, so one way that we can approach a change in entropy is just to go according to two different variables here. So the derivative of the entropy is going to be the partial derivative of the entropy as a function of the volume held at constant temperature times the derivative of the volume. The partial derivative of the entropy function of temperature held at constant volume derivative of temperature. Okay, now we know that basically the volume is going to change because we want to look at the melting transition. So inherently our melting is going to change. So we know that this constant value this constant volume is just not going to, so we can just take that out of our equation right now. Okay, so once we take that change in volume, or the constant volume, because we know our volume is going to be changing because we have, well, delta V. I mean, we're going, the whole purpose is that we're going from solid to liquid. That way we can just say outright that that change in volume, that constant volume doesn't work. So I hope that makes sense, because I want to make it clear that this is not a hand-wavy sort of argument. Oh, we're just throwing out that term because it's we're throwing out that term because it doesn't fit the situation. So of our derivative of yes equal derivative of the entropy with respect to volume temperature, looking at the change in entropy at the melting temperature, and then our dV. Okay. Then we want to multiply T by both sides. So what we get is EdS equals T partial derivative and dV. Okay. So now one of our relations is, and also them are which are very handy in thermodynamics. We have that partial derivative ds dv equals partial derivative dp dt. And I don't want this to be too long, but kind of an exercise there is to actually work unit so you can satisfy yourself that that works. This does seem very hand-wavy right now, but yeah, the units do work out on it, which is what the physics work. I mean, most of these problems can be solved honestly by just looking at the units. Okay, so what I have is T S D V T D V. However, because of this relationship, I'm going to go ahead and dp dt. And that's what our, if you look at the initial form of the Clausius, dp dt. Okay. Now, since we're working with like only one partial derivative here, what we can go ahead and do is say that this is the change in entropy from the initial state to the final state. Go ahead and make this a full derivative. And that's still the constant t, and this is, v final minus v initial. That's the only difference in the term out now that we're not dealing with multiple derivatives, which is nice and helpful. Okay, so now we have our temperature times the change in entropy equals temperature times the slope of pressure as a function of temperature times the change in volume. And I mean, at this point, we can kind of, now let's work off this idea of TDS. So as I said, there's thermodynamics has a lot of these TDS equations. One happens to be TDS equals PdV plus du, where U is internal energy. So we can have our enthalpy, our change in enthalpy, also happens to equal du plus PdV. Haha, you see where we're going with this. So then we have dH equals TS. Haha, and then we have dS equals dH over T. So this brings us to our change of entropy final minus initial equals our delta H over T. And as I'm sure you've guessed right now, delta tends to be also our late. There we go. So our delta H over T equals L over T equals S. So this is, I mean, it's also physically intuitive a bit, and I'm not saying intuitive, it's intuitive as in it's easy. What I mean is that it with this model, that the way that we understand a solid as being something, a particular crystal, a solid is something ordered, and then a liquid is something disordered. This is possibly related to how sometimes you hear people say glass is a liquid, it's not a solid. Well, no, it's a solid, but it's not an ordered solid. It's not a crystal. It's a amorphous solid. And you do have, you can have a transition from an ordered solid, amorphous solid, from a crystalline phase and amorphous phase, and that's going to also have a delta S. And there are other transitions from more ordered symmetries to symmetry that also involve a delta. But let's go on with this. Here, delta S equals L over T. And now let's go back to our T delta S equaled T dP dt. This is what we had originally. Delta V. And just state that these all at a constant temperature instead of writing the parentheses on that with that. Then this is going to go there. So we're going to Tm over Lm equals stuff. And then of course these are canceling. Okay, so those temperatures canceled out, so we get the latent heat equals the melting temperature times the slope of pressure as a function of the melting temperature times the change in volume. Okay, and all we want to do is just rearrange that a little bit. So basically, I mean, for an experimentalist, I'll tell you that it seems a little more natural to express differently because we express it, measure the temperature function of pressure, then we get a curve like that. A little bit more sense that we want to ask this, at least intuitively to me, that we want to express it that way. So that means I'm going to bring it around the equation here, and then we're going to have a V and del V, and then from there we can just see right away that we just completely recovered our Clausius Clayperon relationship. So that's delta V over L. And there we go. There's that's where it came from.